We're going to continue in chapter 14, and we're going to discuss buffers. A buffer is a solution that resists change in its pH. Now, obviously, pH is a change in the concentration of H plus or OH minus. So specifically, buffers resist change in pH when an acid or a base is added. And they do this by actually neutralizing. They actually react with any added acid or base to the solution. Now, like everything else, it's going to have a limit. So at some point, you're going to run out of the stuff that is the buffer, and your pH will change. Most buffers are made by mixing a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. What would that mean? It would mean that if we took a solution, for example, of HNO2 and we mixed it with NaNO2. Now we know that Na plus is inert, and so this is going to be NO2 minus. If we look at this, we have HNO2 and we put it with NO2 minus. This is a weak base. This is a weak acid, and this is its conjugate base. And if we put those two together, we would make a buffer. We're going to realize that this kind of solution will resist change in its pH. Now, doing this is called the common ion effect. Now, the common ion effect means you're starting out with, this is our hydrolysis reaction. I'm using acetic acid. And if I take acetic acid and I put it within water, it's going to make the acetate and the hydronium. So if I have this reaction and I let it work, I'm going to get a certain pH. Now, if I take and I add some of the conjugate base, I'm going to be adding a product. And as the concentration of a product goes up, the reaction is going to shift back towards the original reaction. So the solution will be not as acidic as the original solution of the acetic acid. But we're going to discover that this is going to allow us to have a buffer. Why are we going to have a buffer? Because in the solution, we've got a weak acid and we have a weak base. Weak acids react with bases. So if I add some OH minus, it's going to react with acetic acid. If I take and I add some H3O plus, it is going to react with the acetate. Now, the cool thing about this is what it's going to do, it's going to interconvert them. So if I took CH3COOH and I added some OH minus to it, it would make some water and it would make some acetate. So in my solution, I have now converted a weak acid into a weak base. That has a very small effect on the pH. If instead I took and I added some strong acid, acids are going to react with bases. Now our buffer has in it both the acid and its conjugate base, the weak acid and the conjugate base. So if I add a strong acid to this, it's going to react with the conjugate base. It is going to make CH3COOH, and it's going to make some water. And so if I take a look at this reaction, I'm going to take and I'm going to convert a weak acid into its conjugate base, or a weak base into its conjugate acid if I add something strong. That truly is all that buffers do. So let's imagine here, I know I've got acetic acid here, but let's do a different one. So let's say that we have HNO2 in a solution of NO2 minus. If I just had HNO2 and I put it in water, it would react, two arrows because this is weak, and make some NO2 minus plus some H3O plus. All right, so I've got a nice equilibrium. If I start out with just HNO2, this equilibrium is going to be a fair ways to the right. If I add some NO2 minus, it's going to shift the equilibrium a little bit to the left. So let's imagine now I have both of these in solution. I have an equilibrium. What's going to happen if I take and I add some strong acid? And I can write this as H3O plus or H plus. Well, in my solution, because I have all of these species, my H plus can find something to react with. My H plus is going to react with the NO2 minus, and it's going to make more HNO2. If I added OH minus, it would react with the nitrous acid, my HNO2, and it would make NO2 minus. So buffers just sit there and interconvert between the weak and its conjugate until you run out of one of them. So if we start out with a buffer system where we have equal amounts of the weak acid and its conjugate base, if I take and I add some strong acid to it, acids react with bases, so it's going to react with the CH3COO minus, and when it does, the concentration of that goes down, and the concentration of the conjugate acid, CH3COOH, will go up. If instead I go back to my original equal amounts of weak acid and conjugate base, and I add some hydroxide, well, bases react with acids, so that's going to react with CH3COOH. The amount of CH3COH will go down, and the amount of the conjugate base will go up. And all we're going to do is shift our equilibrium just a little bit. So let's actually just do some math. Now, if I have a solution of just acetic acid, and I've got 0.25 molar, we can do the math on this, and we can get a pH of 2.67. So the question is, what if instead I want to know what the pH is if I throw in some of the conjugate base, if I do this common ion effect? Well, we need an ice chart. So if we have CH3COOH and we allow it to react with water, because remember, everything here is still just a hydrolysis reaction. We haven't actually added anything to change the moles amount of this yet. So we're going to have CH3COO minus and hydronium. We're going to do our ice. We're going to start out with 0.25 of this. We're going to ignore water because it's a pure liquid. And now we've added some of the conjugate base. We're going to assume 0 to start, minus x, 0.25 minus x, plus x. And we know we've got to shift the equilibrium to the right because we have a 0 right here. Can't have zeros in equilibrium. 0.10 plus x and x. If we plug this in to our equation for K, we will get that Ka is equal to 1.8 times 10 to the minus 5, and that's going to equal x multiplied by 0.1 plus x over 0.25 minus x. So what can we do with this? Well, this is small, and small tells us that the x with respect to the initial can be ignored. Well, note we have two x's respect to the initial, and we're going to ignore both of them. No reason to ignore one and not the other, so we're going to ignore both. And when we rearrange this and we solve for it, we are going to get that x is equal to 4.5 times 10 to the minus 5 molar, and our pH is equal to 4.35. So what did we do? Well, we took our equilibrium where we had our weak acid, where we put it in water, and we made the conjugate base and hydronium. And when we took and we added some of this, and the concentration of the A minus went up, the equilibrium shifted in this direction. And now we have a new equilibrium with a pH of about 4.35. All right, what can we do with this? Well, we need some rules first. What do these things do? Buffers resist change in its pH. So I have two solutions here, and they're both at a pH of 8. They have an indicator in them giving that they are the same color. Now, what do I have over here? Over here into my buffered solution, I have added a 1 ml of 0.01 molar HCl, which is a strong acid. If I take and I just put it into a solution that isn't buffered, that's actually quite a bit of strong acid, and my pH is going to go way down. But if I do it into a buffered solution, where it's going to have species in it that resist its change in pH, we're going to see that the color stays the same because the pH stays the same. Our buffer resists change in its pH. If we'll go farther, we need to realize that buffers are all over chemistry and biology and geology, and we've got two blood buffers in our bodies, and we have one of them that's caused by breathing of carbon dioxide, and that's the hydrogen carbonate bicarbonate system, and the other is a phosphate system that's in our liver. I'm going to look at the bicarbonate system. This comes from the fact that when we breathe carbon dioxide, or when we breathe in oxygen, we know carbon dioxide is a byproduct of this, or it's a metabolite or metabolism product of this. Now, carbon dioxide is not carried on the hemoglobin to get back out of the body, like oxygen is carried in, it in fact reacts with the water in your bloodstream. And when it does that, it is going to make carbonic acid. Well, we don't want acids in our bloodstream because we'd like our blood pH to be a little bit above 7. And so our blood counteracts that by also having HCO3 minus in our blood. So our blood buffer system, one of them, is a combination of H2CO3 and a combination of HCO3 minus. If we look at the reaction of this, we have H2CO3 reacts with water to make HCO3 minus plus H3O plus. And this is our equilibrium reaction for this particular buffer. So how does this work? Well, we certainly don't want a massive change in our blood pH. We would really like it to stay constant at a pH in our blood of about 7.35. So if we have our blood system and we add some H plus, our blood becomes acidic. Our body is going to fight that. Well, our body fights that, and notice that this is a strong acid, so this is going to have a very large change in its pH. So if I take and I add my strong acid, it is going to react with the portion of the blood buffer system that is basic, which is this guy, and it's going to take and make H2CO3. So we have just taken our blood buffer and we have converted a strong acid into a weak acid. This would have a large effect on pH, and this would have little or no effect. And that is how our blood buffers work. So we want to be able to calculate the pH of any sort of buffer system. So the first thing we're going to ask ourselves is it a buffer? In order for it to be a buffer, it has to have a weak plus its conjugate. And we are going to consistently be looking at this. If it's got a weak acid and a conjugate base, or a weak base plus a conjugate acid, you're going to have a nice blood buffer system. So we have an equation for this. You can take a look at it in the textbook for the derivation, but our equation is called the Henderson-Hasselbalch, and it states this, that the pH of a buffer system is equal to pKa plus the base 10 log of the concentration of the base over the acid. Now, we're going to use the X is small approximation, which means the concentrations here of the base and the acid, these guys are initial. We consistently ignore that change in X anyways, and this is our equation. And remember that pKa is the minus base 10 log of Ka. Now, this is going to make our math very straightforward using this equation. So let's do this one. So we have a acetate buffer that contains 0.1 molar acetic acid and 0.1 molar sodium acetate. We could do this a number of different ways. We can stop and say to ourselves, okay, well, we have acetic acid, CH3COOH, and it's going to react with water to make our acetate plus our H3O plus. We could do ourselves an ice chart. And when we do this, we're going to get 0.1, ignore 0.1, 0. Now make sure when you do this, you include the original amount of both the acid and the conjugate base. This is going to go down by X. XX, and we're going to get 1.8 times 10 to the minus 5 is equal to X times 0.1 plus X over 0.1 minus X. We're going to set our X equal to 0 compared to the initial. Remember, we're going to consistently do this approximation. When we do this, we're going to get X times 0.1 over 0.1. Notice that these concentrations are equal molar. Those are going to cancel out. And the concentration of the hydronium is going to be 1.8 times 10 to the minus 5 molar. And our pH is going to equal 4.74. You go, okay, I thought you said there was a shorthand. There is a shorthand. The shorthand says, hey, we have a buffer. If we have a buffer, pH is equal to pKa plus the base 10 log of the initial amount of the base over the acid. So pH is going to equal minus base 10 log of 1.8 times 10 to the minus 5 plus the log of the base, which is our acetate, which is 0.1, over our acid, which is our acetic acid. The log of 0.1 over 0.1 is the same as log of 1. Log of 1 is 0, and pH is equal to pKa, and pH is equal to 4.74. Which one do you have to use? Whichever one makes more sense to you. So what happens with these? So what we have here is a solution where we have a weak acid and its conjugate base. If we take and we add an acid, in this case we're adding a strong acid, it's going to react with the A minus to make HA. If we add a strong base, it's going to react with the HA, make more A minus, and these two are just going to interconvert back and forth as we go. When we're going to do our solutions or when we do our calculations, we're going to have to figure out what our new values are of these. And we got to ask ourselves, how well do these work and in what range do these work? Well, we got answers for those. We have buffering capacity and buffering range. Buffering range is the range at which it can be effective. So let's say that we have an acid and the pKa for the acid is equal to 5. The buffering range for this tends to be from about 4 to 6. We can go about 1 pH unit on each side of the pKa. Buffering capacity says how much of added base or acid you can make, or the buffer can neutralize until it's gone. So what do we need? We need to know how much of the weak acid and its conjugate base we have in our solution. That's going to depend on the, or that's going to give us our buffering capacity, and then the pKa of the acid or base is going to give us the range at which it will work.